In section 9.3, we also cover the integral test. It's one of our first formal tests for convergence. So for the integral test, we're going to consider this sum, this infinite series, and if we replace the index k with the variable x, we're going to have a continuous function a of x, and this is also going to be in increasing or decreasing terms. So for example, I've sketched a decreasing continuous function in each of the graphs below. So that's going to represent our function a of x. It's decreasing and continuous from 1 to infinity. And the integral test says if my terms are decreasing and continuous, then the improper integral, the integral from 1 to infinity, a of x dx, and the infinite series, k equal 1 to infinity, a sub k, they both converge or they both diverge. Okay, so what I want to do is sketch a picture to convince you of this. So here I have the function y equal ax sketched. The improper integral would give me the area under this curve. And so if it converged, that area would be finite. I want to show you that this forces in that case, this forces the infinite series to also be finite. So I'm going to sketch some of the terms here. If you look at the area of this rectangle, I'm calculating the height of the rectangle at 2. So the height is a2, the width is 1, so this area is a2. And likewise, if I go to the next increment here and I sketch a rectangle that has height a3, the area of the rectangle is also a3. I just go through here and I continue to sketch these rectangles. That would be a4, a5, and since the function a of x is decreasing, all of these rectangles I'm drawing lie below the curve. Therefore, if I added up all the areas of the rectangles, that would be ak, k equals 2 to infinity. This is going to be less than the area under the curve, which is the improper integral. Therefore, if the improper integral converges, this forces this infinite series to converge. And then I can just add the first term to it, a1, and I get the infinite series that I started with. So this shows that if the improper integral converges, so does the infinite series. Now in the next picture to the right, I want to show the improper integral diverges. This also forces the series to diverge. So I'm going to do this by, again, comparing areas. The area under the curve, in this case, is infinite because we're assuming that the improper integral diverges. Now I'm going to sketch some areas using rectangles. If I project up here to the graph, that's A1, and then sketch the rectangle, the area of that rectangle is A1. Here I project up to the graph, this height is A2. I sketch a rectangle, has width 1, so the area of that rectangle is A2. And I continue to do this, and all these rectangles lie above the curve because once again we're assuming the curve is decreasing. And so what do we see? We see that the sum of all these areas is the infinite series, and this has to be bigger than the area under the curve, which is the improper integral. And this improper integral diverges, so that's going to force this infinite series to diverge as well. So what we've shown with these two pictures is if the improper integral converges, the series converges. If the improper integral diverges, the series diverges. And this is called the integral test. Notice, again, the hypothesis. We have to have a of x is continuous for x greater than or equal to 1, and a sub k, or the function a of x, has to be a decreasing function. Okay, so let's apply the integral test to some examples. In the example 1, this is just the harmonic series. We've already looked at it as an example in class. We know that it diverges, but we're going to show that it diverges using the integral test. So my function a of x, I just replace the index k with x. So my function is 1 over x. If I take the derivative of the function, it's negative. So that tells me that a of x is decreasing. Of course, it's pretty obvious that a of x is decreasing. And 1 over x is a continuous function on 1 to infinity. We're not including the vertical asymptote at 0, so it's a nice continuous function. So it meets the hypothesis for applying the integral test. So therefore, I'm going to integrate my function a of x using the improper integral from 1 to infinity. And that's the limit as b goes to infinity with the integral from 1 to b, 1 over x dx, which is the limit as b approaches infinity, the natural log of b minus the natural log of 1. Okay, and as b goes to infinity, the natural log of b is equal to infinity. So the improper integral diverges. Therefore, that's what these 3 dots mean. The harmonic series, sum k equal 1 to infinity of 1 over k, diverges by the integral test. Okay, let's consider a more general series. And I'm going to change my index to n just to have some variety in the names of my index to get you used to seeing different letters for the index. So in the previous example I used k, this time I'm using n. This is called a p-series because we have the index raised to the pth power in the denominator. So therefore, if I replace my index with x, I get the function 1 over x to the p, which is a power function with a negative power. So if I write that in the numerator, the term in the numerator, it becomes x to the minus p power. If I take the derivative of that, I get what? Bring the power down, raise it to the 1 less power, I get a negative number. So this is a decreasing function, and it's also continuous for x greater than 0. We only need it to be continuous for x greater than 1. So these 2 criteria meet the hypothesis for using the integral test. You should always validate or verify that the hypothesis of a test is met before you use the test. Okay, now let's apply the test. So to apply the test, I'm going to check out the improper integral and see if it converges or diverges. So I'm going to write this as a limit, replacing the upper limit with b, taking the limit as b goes to infinity. I'm going to write the integrand as x to the minus p in power notation. And so this is a power function. The antiderivative is x to the minus p plus 1 over minus p plus 1. I add 1 to the power and divide by it. I'm evaluating this from 1 to b. Okay, so I need to explore this limit. If I substitute in the upper limit, I get b to the minus p plus 1 over minus p plus 1 minus 1 over minus p plus 1. So what does this limit do? Well, it depends upon the value of the power p. So up here I see that if p is bigger than 1, then I'm going to have a negative power. And this b is actually going to be in the denominator. In that case, since b is in the denominator and I'm taking the limit as b goes to infinity, this limit would be 0. If p is between 0 and 1, then this power is going to be positive. And so I get two different cases. This limit is going to be minus 1 over minus p plus 1 if p is bigger than 1, and it's going to be infinity if p is between 0 and 1. So in one case it's going to converge, and in the other case it's going to diverge. Therefore, the p-series will do the same thing. So this series is going to converge if p is greater than 1. And it's going to diverge if p is less than 1, or between 0 and 1. Notice, since the harmonic series is also a p-series with p equal to 1, we've shown separately in the first example that it diverges, and so we can add an equal to sign down here since it diverges if p is also equal to 1. So this p-series is very important, and we can immediately say whether some series converge or diverge just by looking at that value of p. So for example, the series 1 over n squared n equal 1 to infinity, we know that that converges right away because this is a p-series and p is equal to 2. Okay, let's look at another example. So this example, we have the sum of 2 over 1 plus 4n squared. Now notice this is not quite a p-series, although it looks similar to the p-series 1 over n squared. There's some more numbers in it, some more terms in it than that. So we suspect this will probably converge, but we cannot use the p-series as our justification. We're going to use the integral test and analyze this series all on its own. First, we need to validate or verify the hypothesis that the integral test is satisfied. If I replace the index n with x, I get this function. And we can say this is decreasing because the denominator is growing and the numerator is fixed. So as the denominator grows, the value of the function values get smaller and smaller and smaller. So if we take the derivative by using the reciprocal rule or the quotient rule, we see definitively that since the derivative is negative, that this is a decreasing function. And since it's a rational function, it's also continuous whenever the denominator is not 0. So it's, in this case, it's continuous everywhere. The denominator is never 0. So it's a nice continuous function. It's decreasing, so the hypothesis to the integral test is satisfied. Therefore, we're going to apply the integral test. We're going to look at the integral from 1 to infinity 2 over 1 plus 4x squared dx, and see whether this converges or diverges. Again, we suspect it converges since it looks similar to the p-series with p equal to 2. Okay, now we have to actually determine the integral. So I'm going to replace the upper limit with a b, and I'm going to write 4x squared as 2x quantity squared to sort of give you a hint as to how to proceed here. This is a u substitution integral, and we're going to let u be 2x. Therefore, du is 2 dx, and as a matter of fact, I have 2 dx sitting right here. So I have my du sitting there. So I'm going to take the limit as b goes to infinity of this integral. And since I'm using u substitution, I'm going to go ahead and change limits. So I run this lower limit through this transformation, and I get u is equal to 2 times 1. So my lower limit over here is 2. If I run the upper limit through that transformation, I get b, I get u is equal to 2 times b. So u is 2b. And then I have what? Du over 1 plus u squared. Okay, so now I have it set up. I can go ahead and resolve this, the convergence and divergence of this improper integral. So limit as b goes to infinity. Now the antiderivative of 1 over 1 plus u squared is the arctan of u. And I'm evaluating this from 2 to 2b. Taking the limit as b goes to infinity, I'll plug in the upper limit. I have arctan 2b minus arctan of 2. So if I take the limit as b goes to infinity, then what's inside the input of the arctangent is going to infinity. Well, the arctangent has a horizontal asymptote at y equal to pi over 2. So this arctangent of 2b approaches pi over 2 as the input approaches positive infinity. And then the second term, minus arctan of 2, is not affected by the limit. Since this limit exists, the improper integral converges, so the infinite series 2 over 1 plus 4n squared converges by the integral test. Okay, so I think maybe you should see how to apply the integral test. You validate that the hypothesis is satisfied, then you calculate the improper integral of the corresponding function where you replace the index with x. If the improper integral converges, the series converges. If the improper integral diverges, the series diverges. So why don't you work out example 4, pause this, work out example 4 on your own, and when we return, then you can see if you got the solution correct or not. So pause it and work out the example. Okay, so let's see what you did. The function 1 over x, natural log of x squared is indeed decreasing, and the denominator is 0 at 0 and 1. So as long as x is bigger than 1, the denominator is not 0, and it's a nice and continuous function. Okay, so the hypothesis is satisfied. Let's see. We need to integrate. One thing is a little bit different here, that the index starts at 2. So we're going to start our integral at 2 and integrate from 2 to infinity. 1 over x, natural log of x squared. Okay, so this is a u substitution. You should let u be natural log of x. Then du is 1 over x dx. And if we substitute this in, replacing the upper limit with b, we have that this is the limit as b goes to infinity. Let's see, the dx over x is du, and we replace the natural log of x with u, And I need to change my limits. If I run the lower limit through this transformation, I get the natural log of 2. If I run my b, my upper limit through the transformation, I get the natural log of b for my upper limit. So this is a fairly straightforward improper integral now. We're going to take the antiderivative. And so we're going to add, this is u to the minus second power. We're going to add 1 to the power and divide by it and evaluate at the lower and upper limits. So if I plug in, whoops, this is natural log of b up here, not natural log of 2. So if I plug in my upper limit, I get what? Minus 1 over natural log of b. And then I plug in my upper limit, I subtract minus 1 over natural log of 2. And as b goes to infinity, the denominator here goes to infinity, so the whole fraction is going to 0. So I'm getting 1 over the natural log of 2 for the value of that improper integral. So the improper integral converges. Therefore, this series, k equal 2 to infinity, 1 over k natural log k squared, converges by the integral test. Okay, so the only thing different here is we started our lower limit at 2 rather than at 1. So one reason we didn't start it at 1 is because our function would not have been continuous had we started the series at 1, because the natural log of 1 is 0 and we would have been dividing by 0, and therefore we wouldn't have had this continuous property that is necessary for us to apply the integral test. Now, looking down at example 5, maybe pause it and think about that for just a few minutes. If you continue and you apply the integral test, then you're going to do too much work. You ought to be able to look at this and tell that this diverges without applying the integral test. So how do we tell that? By the divergence test, which is the very first test we had. It was in that box in our textbook when we looked at the properties of convergence and divergence. And if we look at the limit as n goes to infinity of the terms, that limit is equal to 1/2 and is not equal to 0. Since the limit of the terms is not 0, by the divergence test, the series diverges. So you want to always be careful about doing too much work. There's enough work to do showing these converge or diverge, and so if there's a quick check that we can use, we certainly want to use that. Okay, so this is the presentation of the integral test. I've given you some examples to work with. You need to try to work some problems yourself, and good luck.